Hi students! In the last video we left off on this slide and we named all of these ionic compounds. And starting off this video I want to point out a couple of things. So we're going to take a look at number 4 and number 7 here. Now, last time we said that number 4 was called iron 2 chloride. And that meant that iron had a charge of +2. So remember, the Roman numeral is there to indicate the charge, not how many irons we have. And we have to indicate the charge because iron is one of those metals that has different charges on different days. So it's called a variable charge. And it's a transition metal also. So we'll often hear it a transition metal with a variable charge, like it says in the rules. Now, the question is, what does iron 3 chloride look like? What's the difference? Well, iron 2 chloride is going to have an iron that's charged with +2, and it's going to have 2 chlorides because those are -1. And a +2 and 2 -1s equal to a neutral charge. Remember, a neutral compound is a happy compound. So iron 3 chloride, how that would be different is the iron would have a charge of what? +3, that's right. So in order to make a neutral compound, we're going to have enough chlorides to equal the -3 to balance the +3 on the iron. Now, chlorides always do a -1, and how we know that is we would have our handy-dandy chart out, and we would see that chlorides do not have a variable charge. They always go -1. So that means if you only had 2 chlorides, like in your iron 2 chloride, you'd have +3 and you'd have -2, having -1 from each of your chlorides. So this means to make a neutral compound, you would need a 3rd chloride. And the formula for that would end up being FeCl3. That is iron 3 chloride. Now, you might think, what's the difference? I don't really need to know that, but indeed they are very different compounds. So from this picture right here, you guys can see with your eyeballs that iron 3 and iron 2 are different compounds, and they're going to have different properties. So you want to definitely make sure you've got the right one. Now, something else I want to point out to you guys is the old school nomenclature. So let me go ahead and erase this right here. Come on, eraser. Erase, erase. Uh-oh, my eraser is not wanting to work today. Okay, so there we go. And let me rewrite iron 3 and iron 2 chloride here since I erased those. So iron 2 chloride has an old school name, as does iron 3 chloride. And these names are still in use. Iron 2, that's going to be ferrous. So right here we have ferrous. So iron 2 chloride, in the old school way of naming it, would be ferrous chloride. And for iron 3, the old way that we would name this is ferric chloride. So iron 3 is ferric, and then chloride is just chloride. So the us ending, it's indicating that you have the smaller charge, the +2. And the ick ending is indicating that you have the larger charge. And for iron, that is +3. Now for copper, that's going to be a little bit different because copper is also a transition metal with a variable charge, but the common charges are +1 and +2 instead of +2 and +3, like with iron. And my cat is telling you guys hello. I don't know if you can hear her, but she says meow meow. So for copper, which we have in number 7, what we have here is a copper 2. So this right here is copper 2 nitrate, because what we have is we have a couple of nitrates, and nitrates are always -1. And how did we know that? Well, we would look at our handy dandy polyatomic ion slide, which is back here, and we can see that our nitrate right here is always a -1. So coming back here, we can see that this is copper 2 because we need a +2 charge on copper to go ahead and balance out the 2 -1 charges on our nitrate. So we have copper 2 nitrate. Now what would copper 1 nitrate look like? Well, if we have copper and it has a +1 charge, all we would need is 1 nitrate to balance out that +1 charge from copper with a -1 charge of nitrate. So copper nitrate, the formula would be written CuNO3. And there are no parentheses around nitrate because when you just have one of them, you don't need to indicate that there's just one of them. So if you have more than one of your polyatomic ions, you put parentheses around them and say 2, 3, 4, whatever it is that you have. Now, like I said with copper, you're also going to have old school naming that is still pretty common these days. And the ending for copper 1, because this is the one in the set that has the lower charge, this one is going to be cuprous. So that has the OUS ending, and that would be nitrate. Now copper 2 is the metal in the set that has the higher charge. So copper 2 is cupric. And what you guys have is you have the ick ending that is indicating that you have the higher charge in the set. So we have cupric nitrate. Okay, so there's your lesson on the old school naming with us and ick. And you guys will see that in your formula writing and your nomenclature assignments. So let's go on to the next slide where we're actually doing some formula writing. So number 8 says, go ahead and write the formula for sodium fluoride. So we've got this ionic compound here and we need to figure out, well, what charge does our metal do? So that's sodium right there. And if we completely forget that sodium likes to do +1, how we would figure that out is we'd go to our handy dandy little chart here and we'd see that sodium likes to do +1. So just to write that under it right here so we can figure out what we're doing, we'll go, okay, we've got a +1 there, and now we need to figure out what charge fluoride does. So going back to our chart right here, we can see that fluoride's always going to do -1. So we have a +1 and a -1. So we need to ask ourselves, how many of each of those ions do we need in order to make a compound that has a neutral charge? Well, if you've got +1 and -1, you just need one of each. So sodium fluoride, how we would write the formula for that would be NaF. And the formula that we see does not include the charges. We just wrote these over here just so we could write down our thought process. So NaF is the official formula for sodium fluoride. Now, number 9 is calcium sulfite. Calcium is Ca, and looking at our chart right here, we can see that calcium likes to do +2. So we can write, okay, we've got +2 there, and then sulfite. What is sulfite? That one sounds a little bit strange, so there should be a bell that goes off in our head that says that might be a polyatomic ion. And if we look on this chart, we can see that indeed sulfite is a polyatomic ion with a charge of -2. So it's SO3 -2. Now, if you have a cation with a charge of +2 and an anion with a charge of -2, how many of each of those do you need in order to have a neutral compound? +2 and -2 add up to 0, so you only need one of each. So the formula for calcium sulfite is CaSO3. And remember, in the formula, you do not see the charges. We assume that the reader can figure out the charges on their own. Number 10 is calcium chloride. Now, calcium we know from number 9 is Ca +2. And chloride is Cl -1. And we've done chloride enough times to know that it's -1, but if you still need to check, go ahead and look right here and see that chloride is -1. So if we've got +2 and -1, the question is how many of each do we need in order to make a neutral compound? Well, if we draw it out in blob form for the visual learners, what we would have is this right here. And you can also put -1 right there if you need it. And a +2 plus a -1 is going to make a +1. And that's not a neutral compound. We need an extra -1 to balance out that +2 of the calcium. So we would need another chloride to come along so that we could say, all right, we're going to add another -1 to that, and then we're going to have 0 net charge there. And remember, a neutral compound is a happy compound. So that means that the formula for calcium chloride would be CaCl, and then we'd put a subscript of 2 down there to indicate that we've got 2 chlorides. Now, the other way that we can think about this is if we've got Ca +2 and we've got Cl -1, we can take this number right here and put it down there, so we'd have Cl2, and we can take this number right here and put it down there, so we'd have 1 calcium. But remember, when you just have 1 of something, you don't need to put the 1 there. So the little switcheroo there works nicely if that's a shortcut that you like to take. But if you're using that, just be aware that it works the best when you have 1s and 2s or 2s and 3s. If you have 2 and 2, you're not going to get the lowest ratio possible, because if you put the 2 down there and the 2 down there, you would get Ca2SO3 2. You'd be saying you need 2 calciums and 2 sulfites. when in reality you only need one of each, so that wouldn't be the lowest ratio. But for 1s and 2s or 2s and 3s on our charges, it's going to work really well. Okay, so calcium chloride, again, how we would write the formula is CaCl2. Okay, so moving on to iron 3 oxide. Now the metals with variable charges are really nice because they just go ahead and tell you what the charge is on your metal. So iron 3 is Fe plus 3. And oxide, that's your ionic form of oxygen. So if you guys don't know right away that oxygen does -2, you can look at the chart right here and see that oxygen does -2. Now, we've got +3 and -2. So how do we get the negatives to equal the positives? Well, we have to go to 6. And what do we multiply 3 by to get 6? We multiply it by 2. So what we will have is Fe2. And then for oxygen, we need to have enough oxygens to where we have -6. So how do we go from 2 to 6? We multiply by 3. So we have Fe2O3. And if that was a little bit confusing for you, there's a couple of different ways to think about it. So we've got 2 irons, so we'd have 2 times +3 because each of our 2 irons has a charge of +3. And we would be adding that to the charge for each of our 3 oxygens. So we have 3 oxygens and they're each a charge of -2. So that makes a +6, and this makes a -6, and that gives us a total of what charge? Yes, we have a net charge of 0, and a neutral compound is a happy compound. If you need to see that in blob form, now this isn't reality, you guys, but I'm just drawing this for my visual learners so you guys can see. You're gonna need 2 iron plus 3s for every 3 oxides, O-2s, okay? And that will give you a net charge that's neutral for your compound. So again, for iron oxide, we've got Fe2O3. Now, the other way, if you're gonna do the little switcheroo thing, this one works really well for, is you would say, okay, let me get the superscript here and make it the subscript there, and you see that right there. And let me get the superscript here without the charges, you guys, because there's no charges in the subscripts. So you put the 2 down there and you see that right there. Okay, so that's a few different ways to think about it when you're trying to figure out what is the formula for iron 3 oxide. Okay, moving on to cobalt 2 hydroxide. So cobalt 2, that's telling us that cobalt has a charge of +2. So we have big C, little o for cobalt, and that's +2, and then hydroxide. What on earth is hydroxide? Ding, 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 that must be a polyatomic ion. So let's go to the chart and see if we can locate that. And there it is right there. Hydroxide is a polyatomic ion with a charge of -1. So that whole package, OH, has a charge of -1. So we have OH of -1. Now, how many of each of these do I need to make a neutral compound? Well, if I've got +2, I'm going to need to balance that with -2. So I must need 2 hydroxides. So how I would write that is cobalt, and then I would put parentheses around my hydroxide. And remember, again, when we're writing formulas, you do not put the charges in there. And you would say that you need 2 of those. So again, when you have a polyatomic ion and you have more than one of them, you need to put parentheses around the formula for the polyatomic ion and put how many of them you have. You do not want to write this as this. That's not the same thing. H2O2 is hydrogen peroxide. That is completely different than having 2 hydroxides. The other way we could do it, you guys, is the little switcheroo, where you take the superscript and make it the subscript there, and the superscript here and make it the subscript there. So with the 2, you can see it shows up right there. And with the 1, it's there. We just don't put it because convention says when it's 1, we don't need to write it. So the formula for cobalt 2 hydroxide is COOH2. All right, ammonium bromide. Ammonium is the positive polyatomic ion that you will see the most. So it's NH4 positive, positive 1. So ammonium is NH4 plus 1. And bromide, that's a halogen. And all of our halogens are always going to be -1 when they're ions. And if you guys don't believe me, just go ahead and take a look at this chart. And you guys will see that bromide is Br -1. So we've got Br -1 and NH4 plus 1. Now, if you get a +1 and a -1, how many of each of those ions do you need in order to make a neutral charge? 1 of each, that's right. So you just go ahead and write NH4 Br. That's ammonium bromide. Now, number 14 is ammonium carbonate, and we already know what ammonium is because we did it in number 13. And then carbonate, that is not the ion for carbon. That is a polyatomic ion. And that's one of the ones that you should get to know. That one is right there. It's CO3 -2. So just to write it here, to put down our thought process, we'll put NH4 plus and CO3 -2. Now, if you have one ion that has a charge of +1 and another ion that has a charge of -2, we again need to figure out what the ratio is of these two things so we have a net neutral charge. Now, if we've got a -2 here, then we need to have +2. So that brings us to the question, how many ammoniums do we need? 2, that's right. Now, ammonium is a polyatomic ion, so if you have more than one of them, you need to put them in parentheses and indicate with a subscript how many of them you have. So we said that we need 2 of those in order to get to +2. Now, again, remember you don't put the charges there when you're writing the formula. And above, we saw that we did not need parentheses for ammonium, and that was because we just needed 1 of them. So ammonium carbonate is NH4 in parentheses, and then the 2 down here to indicate that you need 2 of them. And then you just write carbonate, and you don't need to write parentheses because why? Because you only need 1 of them, okay? So if you guys wanted to do the switcheroo thing, you would see that you needed 1 carbonate and you need 2 ammoniums. Now, if we wanted to write that out in terms of algebra, we'd have 2 ammoniums. They each have a +1 charge, plus 1 carbonate that has a -2 charge, And that's going to give us a net charge of 0, and a neutral compound is a happy compound. Yay! Okay, last one on this slide. We have aluminum carbonate. Aluminum is Al, and if we're looking to see what charge it has, this little chart right here will tell us that it is +3. Aluminum likes to do +3. So we have Al +3, and on number 14 we discovered that carbonate is -2. So, oh no, we have the 3 and the 2 situation again. So we need to go up to +6 and -6. Now, how many aluminums do you need in order to get a charge of +6? You're going to need 2 of those. That's right. Now, how many carbonates do you need to get to a charge of -6? You need 3 of those. So you're going to put carbonate in parentheses because it's a polyatomic ion, and you're going to put 3 there. Now the other way we can do it, again, is with the switcheroo thing. So we have the 3 there, and that would go down there, and you guys can see that right there. Do not confuse that with the 3 that is already there for the carbonate. You want to say that you have 3 CO3s, and with the parentheses, that's how you do it. And the 2 goes down there for aluminum, okay? And we can see that is right there. If you want to look at it in an algebraic way, you need 2 aluminums, and they both have a +3 charge. That would give you a +6 total. Plus you need 3 carbonates that each have a -2 charge. And that one is going to give you a total of -6. And this is going to add up to 0. And a neutral compound is a happy compound. Okay, so that is the end of that slide, which brings us to covalent compounds, which is another type of compound that we need to name and learn how to write the formulas for. But I will leave that for the next video that you should watch also, because you're going to need that for formula writing and nomenclature online assignments. Okay, until next time, bye-bye.